privacy, machine learning, algorithms, and data structures. He's a research scientist at Apple, and he got his PhD from UC Berkeley in 2004 and was at Microsoft Research from 2004 to 2014, and then Google Brain from 2015 to 2019. And today he'll be talking about sampleable anonymous aggregation for private federated data analysis. Kunal, please take it away.
Okay, can you hear me okay? Perfect. All right, so yeah, thank you for the invitation. It's really great to be here. Guess today I want to tell you about this rather complicated title. So I guess most of my talk will be about what this title means and why we are interested in it. And I'll spend a little bit of time talking about how we actually implement this object that I'm talking about. All right, so let me start with thanking all the collaborators that made this work possible. So I'll be talking primarily about the first work here, which will be at CCS in a couple of months. And I'll touch a little bit upon this the second piece of work that was just presented at Usenix. Both of these are on archive, so I guess all of the details that are not in the talk will be in the papers there. Good. Okay, so let me start with the motivation. So we have devices. Devices have data on them. So for example, these phones may know what are the most popular emojis that are used on each of these devices. And we would like to learn from them. So we would want to, for example, figure out that certain emojis are more popular than others, and perhaps use that in a predictive keyboard. But of course, in many of these cases, the data that's on these devices, this useful data that we are talking about, is also sensitive data. Right? And I guess the premise of federated learning is that we address this problem of learning from sensitive data by making sure that that this data stays on devices. It's never brought to the server. This is a form of data minimization. And we essentially run some distributed computation to still be able to learn from this data. Right? And I guess this case of statistics is one example. More generally, we may want to train a machine learning model on this data. And I guess this distributed setup and modern machine learning algorithms such as stochastic gradient descent are very well suited for this purpose. So devices can the server can send a model down to the devices can compute the gradients, send back the gradients, the server can apply those gradients, and then we can repeat this process until the model converges. Right? And that's basically what federated learning looks like. So are we done? And I guess, of course, for this audience, it should be clear that we are not done, because models, while we have made sure that the data stays on the device, the models themselves can memorize this training data. Right? And in fact, this is not just a hypothetical concern. In the centrally trained setting, at least, there's a lot of evidence, a lot of work showing that you can actually extract training data from machine learning models. Right? So we want to also protect from that. And differential privacy is a way to address this concern. So differential privacy formally gives you a measure of how much information is leaked by the computation, by the output of the model, how much information does it contain about individual training examples or data from individual users. And I'll not get into the definition today, except to say that differential privacy provably prevents memorization. In fact, something even stronger is true. A differentially private model will provably prevent what's known as a membership inference attack, where you're trying to distinguish a model that has used a certain user's data from a model that hasn't. Good. So I guess that then suggests a natural strategy. We will train using federated learning to keep the data on devices, and we'll use differential privacy, differentially private training, such as the kind of algorithm Yang-Sibo talked about, to make sure that the model cannot memorize training data. Good. So now you can then ask, okay, if we do these two things, are we done? Can we are we ensured that user privacy is protected? And I guess the answer to that really depends on the trust model. So in this case that the central server that's running this computation is trusted, we are in fact done. And if it's not trusted, then in fact, you can imagine that attacks are possible. And indeed, these papers show that that it's not very hard for an adversarial server to corrupt a computation so that they can learn about an individual user. So the question we want to ask today is, can we reduce or eliminate this trust assumption? Can we get away from having to trust the central server? And of course, this is not a new question. This goes back to the very early days of differential privacy. And what people showed back, and I guess from the very early days, we have looked at two different models of differential privacy. There's the central model, where we have a trusted curator. On the left here, so we make sure that the output that goes out from this trusted curator is sanitized to protect privacy. But people have also looked at what's known as the local model of differential privacy, where everything that leaves an individual device or an individual contributor to this database, that's already sanitized to ensure differential privacy. Right, so we could, of course, just go entirely to the local model. But what the theory of differential privacy also tells us is that the utility gap between these two is enormous. So we'll come to that more precise quantitative versions in a little bit. But I guess in short, if you want to train a machine learning model, in this model, it's pretty much almost impossible to train all but the simplest of models. Okay. But again, I guess I'm talking to a group of cryptographers here. You would say, well, anything you can do in the central model, you can just simulate one central curator using crypto. And in fact, very early work in differential privacy sort of talked about that. I guess so Dwork et al. Argued that you could essentially simulate a central curator by using an MPC over all the clients. And in principle, that completely solves the problem. I can get the accuracy of the central model without the strong trust assumptions that it entails. However, in settings of the kind that I'm talking about today, this is not really feasible for a number of reasons. The number of devices we are running the computation on is often very, very large, like in the millions to tens to hundreds of millions. And general purpose multi-party computation just doesn't scale to these very large numbers. And additionally, I guess we'll be concerned about a few different desiderata that I've highlighted here. The devices that we want to work with usually have limited communication bandwidth. So you can't expect each device to communicate with all of the other devices, for example. They're also restricted in terms of the amount of computation they can do. And finally, when we talk about a large number of devices, we cannot really expect all of them to be honest in the sense that they are really running the protocol. So we want to be robust to some small fraction of the clients being adversarial and trying to disrupt our computation. So when we put all of these constraints, general purpose MPC becomes very difficult to scale. And so it makes sense to do something simpler, which is to not do general purpose MPC, but to do sort of to implement specific kinds of primitives. So one approach that has been very popular is to say, I don't want to general purpose MPC to convert any arbitrary differentially private algorithm to a distributed MPC protocol, but I'll implement a certain primitive. I'll make sure that that primitive is implemented in a scalable way. I will thoroughly vet the assumptions that go into the security of the primitive. I'll thoroughly vet the implementation. And then once I'm sure that this primitive is actually correctly and securely implemented, I can build private algorithms on top of that. Right? So you'd want a primitive that on the one hand is simple enough to actually implement, but you also want that this primitive is rich enough to enable a large class of computations that we care about. So I guess an early example of such a primitive, which kind of goes back to the early, goes back to a long time in crypto, and I guess has been suggested in these works in the privacy setup, is shuffling. So imagine I have a shuffler which can essentially take a bunch of messages, but then shuffle them together and give them to, and ensure that the only thing an adversary sees is a random permutation of all the messages that were sent to this primitive. It turns out that for many tasks of interest in differential privacy, shuffling is actually a pretty powerful primitive. So here's an example. This is the task that we kind of alluded to very early in the talk, which is that of building a histogram. So imagine I want to understand which are the most popular emojis. More generally, each device has some single value from some alphabet k. And my goal is to build an approximate histogram over these k values. So I want to count for each possible value in k, how many users have that as their correct value, that as their preferred value. There's multiple ways you may want to measure the error of your histogram. One particular useful measure is the L infinity error between the approximate private histogram and the true histogram. And I guess this one does exhibit this very large separation. In the central DP setting, this utility is roughly 1 over epsilon. I'm ignoring log factors throughout this talk. In the local setting, we know you cannot do better than square root n over epsilon. So there's a huge gap here. And after a long sequence of works, we were able to show that in the shuffle model, you can essentially achieve the same bound as the central model. So if the task you care about is histograms, the shuffle model is actually pretty good. All you need is a shuffle primitive. In fact, we can do this, not just get the right accuracy, but also do well on the other desiderata that we talked about, low communication, low cost. So for histograms, this is good. But of course, histograms is not the only thing we care about. Here's one more task that you may be interested in, which is what I'm calling vector aggregation. So this is the task you want to do, for example, if you want to run gradient descent, where each user, each device has a vector. We'll assume those vectors have bounded L2 norm. They're in some d-dimensional space. And our goal is to estimate the sum of these vectors. Now, again, there's a large separation between what we can do in the central model, where you can get L2 error roughly square root d over epsilon, versus the local model, where you have to pay a square root n overhead. Once again, right? So again, these two are far apart, provably so. And you can ask what happens with the shuffle model, right? Is shuffling enough to solve this task? The answer here turns out to be a bit more complex. So here's what we know. Even in dimension 1, if I restrict each user to send a single message, there's a polynomial overhead that you must pay. There's a square root, there's n to the 1/6 term that shows up. This you can address using a little more than one message. If you let each user send 2 or even 1 plus a little of 1 messages, you can get the central accuracy for dimension 1. But if you increase the dimension, if you look at arbitrary dimensions, things get complicated. With single messages, high dimensions, you basically end up with the square root dn bound that we had in the local setting. And to actually get anywhere close to the central model, the number of messages needs to be about d per user. So what we showed in this recent work is that any algorithm in the shuffle model, which is restricted to send, which if the algorithm gets accuracy that's close to the central model, each user will have to send d separate messages. And that's pretty large. In fact, if you add in the robustness constraint that we care about, this basically becomes infeasible because you need to validate d contributions from each user, and that incurs a very large overhead. So I would say the upshot of this is that if you wanted to solve aggregation, vector aggregation in high dimensions, the shuffle model is just not going to give you a feasible protocol. Okay, so what do we do? I guess we need to expand our primitive, and the most natural thing to do is to add in the task we can't do, right? So aggregation is something we can imagine developing as a primitive, and of course, if you write down an aggregation, if you have an aggregation primitive, you can do aggregation, right? Good. So I guess that's another primitive which has been studied. People have talked about it. And of course, with this aggregation primitive, we can not only do this task, we can also show that you can, if you add in some robustness that we'll talk about a little bit later in the talk, we can actually satisfy all the desiderata that we care about for this kind of problem. Good. So let me then talk about one more task that we are often interested in, and that will partly motivate the new primitive that I'm talking about. So this is a task that I'm calling the counting needles task. So I guess you may have heard of the problem of finding needles in the haystack. Often what we are interested in doing is not just find needles, but count how many needles there are of each color, right? So formally, we once again have the same setting as the histogram, except that there's some default value, the hay value, that pretty much all the inputs, or a very large fraction of the inputs, have this one default value. So imagine we are trying to learn error codes. Most of the time, the app works flawlessly, so there's no error code. That's kind of the default value. And we are interested in learning the distribution of the error codes when there is an error. So this is, of course, a special case of the histogram task. So everything we said for the histogram case works here. Is the problem solved? I would argue not quite, because if I didn't care about privacy, what I would do is only send the error code when it's different from the default value. So instead of n devices having to send messages to the aggregator, only gamma times n of them will send the message to the server. So gamma here is the fraction of non-default values. Whereas if all you have is a shuffler or an aggregator, this is provably, you pretty much provably need n messages if you want to do this with privacy. Okay, so this motivates the new primitive that I'm going to define. It's what I call an anonymous aggregator. To first approximation, it's what the name suggests. It's an aggregator that provides anonymity. So what does that mean? We have n possible users. Each user has some input. The user will themselves decide, perhaps based on their data xi, whether they want to send the message or not, whether they want to participate, whether they want to add themselves to this special index set I. And the functionality says that if the number of users that decide to participate is at least some threshold B, then this functionality will give you the sum of whatever your some encoder applied to the inputs. Right, so I have my input xi. If I decide to participate, I will apply this function r to my input and send it to the aggregator. The aggregator will only provide an output if a sufficiently large number of users participate. And more importantly, the set I remains hidden. So this is the anonymity property we wanted. Good. So it turns out that this anonymous aggregator actually suffices to solve the counting needles task with only about gamma n messages. So with this, we can actually implement some kind of importance sampling and ensure that the number of messages doesn't need to grow with n, but only with gamma times n, and still get the same kind of accuracy guarantees as the central setting. Once you have an anonymous aggregator, you can also use it to implement what I'm calling a sampleable anonymous aggregator. So sampleability basically just means that the set of users that are contributing is a random sample of all the users. And I guess I will not have time to get into this, but the differentially private SGD algorithm that Yang Sibo talked about earlier, and is kind of the standard algorithm for private machine learning, the analysis of that requires this property that the set of users that participate in each round of the algorithm is a uniformly random sample of all the users. And I guess essentially what this slide is arguing is if you have an anonymous aggregator, you can essentially have each device toss a coin and get a sampleable anonymous aggregator. We can implement this random subset, sum over a random subset. Here is a quick graph to compare how much we can gain from this. So I guess here I'm plotting. So here I'm looking at a setting for the counting needles task where we have n users. So n is like, say, 10 to the 7. I have an alphabet of size k, which is, I guess, 1,000 here, 10,000 there. Gamma is 0.01. The black line there is what we would get without privacy if we just did random sampling. So I'm plotting the communication, the number of devices that I sample. That's my communication cost versus the variance of the estimate. Both of these are on a log scale. So I guess the black and the blue are the non-private algorithms, the black being the uniform sampling version and the blue being the importance sampling version. So as you can see, being able to importance sample non-privately gives you a very significant improvement in the trade-off between variance and the amount of communication. And I guess the red line is what you would get if all you had was an aggregator. The green line is what we get if we have a anonymous aggregator. Right? So for at least some reasonable settings of parameters, you can see that an anonymous aggregator allows us to do much better on the counting needles task for the same amount of communication. Good. So I guess that's kind of the motivation for why we want to build an anonymous aggregator. Let me spend a little bit of time talking about how you could build one. So one way to build one that we talk about in the paper is to build on top of the PRIO protocol by Corrigan, Gibbs, and Bonnet, which essentially uses a two-server trust model or two or more servers. So I guess each device will take the input that they want to share. They will secret share it using additive secret sharing to two or more servers. the servers each aggregate the shares that they get, and then you add up the sums of the shares, and that basically gives you the sum of the contributions. And as long as at least one of the servers is honest, you get the property that nothing except the aggregate is learned. Right? And I guess the thresholding that we needed to ensure that the batch size is large enough, the number of contributions is large enough, that's very easy to implement by having each of the servers ensure that they only return a result if sufficiently many users contribute. This algorithm is very scalable. It has been used in many cases by Firefox for exposure notifications analysis, and it has been used to aggregate tens of billions of reports in sort of existing published work. And I guess what we argue in the paper is that if you combine this PRIO architecture with two additional components, the first is what I'm calling an anonymization infrastructure. So this is some infrastructure that ensures that we can disassociate messages from their senders. So these objects exist. You can build them on top of, for example, onion routing is one such way to do it. There's the oblivious HTTP protocol, which is an IETF standard, which provides this functionality in a scalable way. And the second additional primitive we need is some kind of an authentication infrastructure. So this authenticates that the message is coming from a real device. And I guess this again is something that has been built in a scalable way. There's the privacy pass protocol that essentially standardizes a token scheme, an authentication scheme. And I guess what we argue in the paper is that if you combine PRIO in the very natural way with these two primitives, you get an anonymous aggregator. I guess briefly, the anonymizer basically gives you the anonymity, and the authentication is needed to ensure that to protect against Sybil attacks. The other advantage of using a PRIO-like scheme is that we can add the robustness property that we wanted to it. So PRIO allows zero knowledge proofs that so the client can convince the two provers that their contribution is a valid contribution for various notions of validity. So that makes the system robust to adversarial clients. Right? So for example, if you're doing machine learning, you want to ensure that each client's contribution is actually a vector with bounded norm, and we'll talk more about that in a few minutes. That's a property of the contribution. The PRIO kind of setup allows us to give a zero knowledge proof that this property holds for the input. Right? So this ensures that an adversarial client cannot corrupt the machine learning process by sending an arbitrarily large gradient. And I guess there's a large body of work on sort of designing these validation proofs for various kinds of primitives that you may be interested in. Okay, so let me then spend a little bit of time talking about one specific, about the second work, where we design more efficient protocols for one specific primitive of interest, which is the Euclidean norm. So just a reminder, when we are doing gradient descent for federated learning, each client has to contribute a gradient vector. Typically, when we are doing this with privacy, we clip the norm of this gradient vector to be some bounded value. Let's call it 1. And the problem we are worried about is that an adversarial client can poison the computation by sending a vector that's much larger than norm1. So our goal is to, in the PRIO type framework, give a distributed zero knowledge proof that a vector has bounded L2 norm. Right? Of course, we can't aggregate real vectors in any in PRIO. What we can aggregate is integer vectors, or actually finite field vectors. So we'll essentially round real vectors to integer vectors. So we'll think of V as a vector in Z to the D. Let's say it has some B bits of precision. So it's between, each coordinate is between 0 and 2 to the B. And my goal is to prove that the sum of the squares of these vectors is bounded by some value capital B. Right? So this is not a new problem. This is something I can build a circuit for, and therefore PRIO can let me validate it, except that all these operations are over the finite field. Right? So all I'll be validating is that a property like that holds over FQ. So the existing approaches kind of need to deal with, so I guess what we need to do is deal with the fact that the vectors I have are real vectors or integer vectors. I want to verify an inequality over integers, where all I can do is verify properties over the finite field. So the existing approaches basically say, okay, I have this vector. Let me send each bit of this vector separately. I can validate the property that each bit, when secret shared, is still a bit. So I can ensure that what I'm secret sharing is actually either 0 or 1 over the finite field. And that works. Then I can validate this property, except that now I'm sending, instead of D finite field values, I'm sending D times B finite field values. Right? So think of B as 15. So I'm sending 15 times as much data as I originally was. And I guess there is work. There's a couple of works, PRIO Plus and ELSA, where they improve on this, where they allow us to send D times B bits instead of finite field elements. But the downside of that is that these works require us to send to do a very large amount of server-to-server computation. So we save on the client server computation, but we do an equivalent amount of server-to-server computation for each element. So I guess this is the problem that we address in this work called Pine. So we will continue doing secret sharing over the finite field. So the original message that I'm sending, I have a B-bit message. I encode it as a finite field element and send it. So just the data itself requires me to send D field elements. And what we show is you can design a proof where the additional amount of communication for the proof is only scales as square root of D. So roughly, this is how it works. So existing work on fully linear PCPs by Bonnet et al. Shows that you can validate an equality over the finite field. So what that tells me is that sum of Vi squared is equal to B when I look at it as finite field arithmetic. So mod Q, this equality holds. The challenge, of course, is that the adversary can make sure that this equality holds when the sum of Vi squared is actually B plus Q. Right? And I want to distinguish between the good case when it's actually B and the bad case when it's B plus Q or B plus some multiple of Q. And I guess our work basically builds on the following lemma. It says that if you pick a random Z, so Z is again a vector in, so Z is now a vector in -1, 0, or 1 to the D. And look at the dot product between Z and V. then in the good case, this dot product is almost certainly not very large. It's about square root b. Whereas in the bad case, there's at least a probability half that this dot product is large. So if I take my finite field to be large enough, I can basically make these two cases distinguishable. I can repeat this proof a few times. This inequality check I can reduce to an equality check with a little bit more work, and again then use the fully linear PCP's machinery to solve this. And what we can show is that the overall communication required in this approach is only about square root t. We also give a different approach. So I guess there's, instead of requiring fully zero knowledge, you can just require what we call differential zero knowledge, where essentially the zero knowledge condition gets replaced by a differential privacy-like condition. And that's enough for all of these applications where eventually what we care about is differential privacy. And that's another approach which gives kind of similar overheads, sometimes slightly better. I'll not get into that. Just to show some numbers, if we have a 64-bit field size and D is in the millions, the overhead of the existing approaches would be like 15x, or multiple large, some very large constant. The overheads in our approach are only a few %. So this is not just square root D in theory. If you put in concrete numbers, this is actually something that's very practical. Good. Okay, so I guess that's mostly what I wanted to tell you about. So hopefully I've convinced you that sampleable anonymous aggregation is a valuable primitive. And using it, we can get central-like accuracies for many different tasks of interest. We can implement it without strong trust assumptions in a robust way, and in a very scalable way. And I guess indeed this sort of scalability has been demonstrated by existing implementations of Trio. And yeah, I guess I'll stop here. I guess the papers are here. If you have more questions, I'm happy to answer those. Yeah.
Any questions? Are there any you think are there any?
Can you elaborate on what you mean by
Sure. Yeah. So I guess so let's see. So I guess let me start with sort of the motivation. So I guess in all of this setup, we are talking about a case where I have an input. I send this input to this aggregator, and the aggregator outputs nothing but the aggregate. And while that's a nice condition to have, if we really care about privacy, we have to ask also, what does the aggregate reveal about my data, right? Yeah. And normally the way we address that question is we say, well, we'll add some noise to the aggregate before releasing it. So what you learn is not really the aggregate, but a noisy aggregate. And the noisy aggregate satisfies differential privacy. So at the end of the day, the assurance I have as a contributor is not really zero knowledge. It's actually differential privacy. So then you can go back and say, OK, if that's really the assurance that I get eventually, maybe I can just relax the zero knowledge condition itself to say that that from the viewpoint of any adversary, I satisfy not semantic indistinguishability, but a differential privacy condition. So formally we say that this protocol is differentially zero knowledge if the likelihood of any transcript, if my data is X, is within an e to the epsilon multiplicative factor of the probability of the same transcript if my data was Z prime. Right? So that's basically what differential privacy zero knowledge is, and yeah.
Any other questions? I had a question actually. So for this like color the needles application, you said it's for like error codes from users. So I'm assuming like it's probably not just like a binary like 0, 1 for the error codes, right? So is there a
Right.
reason why you like take this kind of approach instead of something like a DP histogram or something like this?
Yeah, so I guess it's basically a DP histogram. We basically may have multiple error codes. The assumption we are making is, or the constraint we are interested, or yeah, the assumption we are making is that most of the time there's one specific default value. When it's not default, we need to learn the distribution of the non-default values. So I'm interested in the distribution over non-zero error codes. And I guess the main point is we don't want to waste communication by having most of the devices send a message saying no error code.
All right, let's thank Kunal again.